Howdy howdy, this is Mr. Potter. As you've undoubtedly figured out, last video was an April Fool's video, so let's go ahead and talk about why these mathematics just don't work out. So the first thing that we did is we proved that 1 was equal to 2. And of course we started off with this assumption that A equals B. Well, if A equals B, then dividing by this expression here is going to be problematic, because if A equals B, then A minus B is equal to 0. And even if I take A times A minus B, which is what gave us our A squared minus AB, this is still going to be just A times 0. So this is still 0. And so here we were dividing by 0. So that was the problem with this 1 equals 2. So a simple algebra issue. And it's something we have to watch out for in our algebra classes. We need to make sure that we don't have any division by 0, because it means that whatever algebra occurs afterwards is questionable. So for the second proof, we proved that 63, 64, and 65 were all the same number. And the issue actually has to do with these shapes. So let me take a look at these shapes separately. So here's my first shape. And one of the things that you will notice is that this shape, this slanted line, really does go over. Let me move this over just so it aligns with these graph paper. Notice that it goes over 2 and up 5. So this line actually has a slope of, well, 5 divided by 2 is about 2.5. And if I take a look at one of these other lines over here, notice that this is really going over 3 and up 1, 2, 3, 4, 5, 6, 7, 8. So 8 divided by 3 is 2.6 repeating. And the issue is that these slopes are not the same. So when I had these shapes over here, I had this shape here and this shape here, because these slopes weren't the same. I've actually got overlap. There's a real thin area of overlap right here that you can't see just because of the way it is. But these lines are overlapping, and the overlap here and the overlap here on this one actually adds up to 1 full square. And so 1 full square is basically being counted twice in this shape. 1 full square is being taken away from the 64 to give us 63. Similarly, oops, let me get the triangle here, or the trapezoid. Over here, when I make this shape, again, these slopes aren't going to line out, but now I actually have a gap that actually shows up. And this gap has an area of 1 unit. I just want the triangle. Give me the triangle. And so this gap is going to have an area of 1. And so I've exaggerated the gap here, but you can see here that I do have a space in between here. And it's because these slopes just don't match. So here I'm actually adding an extra parallelogram or rhombus here that has an area of 1 cube, and so I'm really adding 1 to the cube here. Here I was subtracting 1 because of overlap. Here I was adding 1 because of this gap, and that's all because these slopes aren't the same. Now I was using, I don't know if you've noticed, but we've got 3, we've got 5, we've got 8, we've got 13. I'm using Fibonacci numbers here, and the fact that Fibonacci numbers give us this nice property really do help out. All right, for the imaginary problem, here we ended up proving that 1 was equal to -1. And the issue with this is the idea that when I take the square root of a fraction, normally we say that it's the square root of the numerator over the square root of the denominator, but this is only for real numbers. It's not going to work for imaginary numbers. As a matter of fact, if I ever end up with an I in the denominator, I can multiply the top and bottom by I to the 4th, multiplying the top and the bottom by 1. And what actually happens here is I end up with an I cubed. And this I cubed is really -1. So 1 over I, negative I. And so 1 over I is really equal to -I. And so this is where the additional negative sign actually gets inserted. It's actually this step where I went from having a radical of a fraction to the radical of the numerator over the radical of the denominator. It works for real numbers, it just doesn't work for imaginary numbers. And so it's something that we have to watch out for. And now probably the most trickiest problem, proving 1 equals 2 using calculus. And there's a couple of issues here. The first main issue is that when I look at y equals x as a graph, my graph actually looks something like this, which means that I actually have between these integers, I've actually got other points. The problem is when I do this breakdown, I'm limiting myself to just whole numbers, to just integers. Because if x is equal to 6.5, I really can't say it's 1 plus 1 plus dot 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 plus 1 6.5 times. And so this is the issue of discrete versus continuous. So this is one part that I've got a problem with. The other part, of course, is when I actually multiply by x, this, because this number here is x, I have to use the chain rule when I actually take the derivative. And so I'm going to have x times 1 plus 1 times x, which actually ends up giving me the 2x that I want. And so I actually end up with 2x equals 2x here. And so I end up with 2 equals 2. So the issue right here, the main idea, the main problem with this is this concept of discrete versus continuous. So, of course, all of these are mathematical untruths. And I figured that April Fool's was the perfect time to bring these out. But I do want to wish you a happy post-April Fool's Day. Just don't believe everything you see on the internet. Once again, this is Mr. Potter. Thank you for watching. Have a great day.